Hey there, ladies and gentlemen, and all the other people that doesn't apply to. We're gonna go over the answers to worksheet 2. It's gonna be a dynamic, exciting. I mean, we're gonna talk about electrons. We're gonna talk about atomic radii. Whoa! You're already falling asleep. That's not cool. Okay. So let's go ahead and get started. Our first question on worksheet 2 was about as elements of period 2 are considered from left to right, there is an increase in the answer was ionization energy. But if you don't know what the heck ionization energy is, that wouldn't matter. So I'm going to go through and explain what these four terms mean using this giant, awesome periodic table. And I like this periodic table because A, it's got the elements on it, and B, it's got all of the orbitals and energy levels and sublevels. I mean, sublevels and energy levels kind of hiding on it. So first of all, there are four terms we talked about in the notes the other day. Atomic radius is the one we're going to start with. This is how big is an atom. And there's two ways to look at all of these, and that's as you go down a group versus as you go across the periodic table. So usually we'll start with going down a group. As we go down a group, we're going from the first energy level to the second, to the third, to the fourth, the fifth. And with each energy level, we are growing in size. 1, 2, 3. We're growing in atomic size or atomic radius. And that usually is very easy for kids to understand. As we go from one element down, gets bigger, down, gets bigger, down, gets bigger, because we're adding energy levels. Cool. Gets bigger as we go down. As we go across the periodic table, we are the same approximate size. All of these elements are on the fourth level. Fourth level. So this approximate size doesn't change. But what does change is those number of protons. 19, 20, 25, 31, 36. And as we go across the periodic table, the protons pull that energy level in, and so size gets smaller, or the atomic radius gets smaller as we progress to the right. So the smallest elements on the periodic table in terms of radius and size are over here, particularly helium. And then the biggest element on the periodic table is over here, francium. So He is small and so strong. He is small, and France is fat. Small, big, whatever. So that's atomic radius. What is shielding effect? Shielding effect is the effect that these electron rings have on the outside. So say this is the outside, and you have the nucleus in there. Let's pick a different color. Here we go. The nucleus in here pulls on all these energy levels, and it's pulling them in, and it's pulling them in, and it's pulling them in. But the energy levels themselves repel each other. And therefore, while the nucleus is pulling in, the electrons are pushing out. We call that shielding. They're shielding each other. As we add energy levels, we add more and more layers of shielding. So the seventh level is shielded by the first 6 levels. So if you had an element like barium, which has 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 6s2, it's got all of those layers of electrons shielding the nucleus from the outside. All right, so shielding effect increases as we go down. Now, as we go across, shielding effect actually doesn't change at all. Not at all. Because the inside layer is not changing at all. When we go from potassium to calcium, we still have the same inside layer. We go from calcium to germanium, still the same inner layers. We still have 3 inner layers repelling that 4th layer we're building upon. Okay, let's get rid of all those annotations and talk about ionization. Ionization is the energy to remove. We're trying to remove an electron. And this actually follows a similar pattern to atomic radius. As we go down, these elements keep having electrons farther and farther and farther from the nucleus. And whatever electrons on the outside is repelled by all these inside ones. So this electron that's maybe 4 layers out is going to be easier to remove on the 4th level than one that would have been only on the 2nd level. So as we go down, the energy to remove an electron slowly decreases because they're farther and farther and farther away. As we go across, though, as we go across the periodic table, we're adding protons, adding protons, adding protons, adding protons, adding protons, adding protons, and the protons pull the electrons, so the ionization energy slowly increases. So going across, ionization energy increases. Going down, it decreases. So the energy to remove electrons would be the highest over here for helium, in this corner. That would be the highest energy to remove electrons. And again, it'd be easiest to take from the French over here. Metallic characters, not terribly exciting. We had that like stair-step break here. These elements over here are not like metals. These elements this way are like metals. Again, as you get closer to the left, they're more metallic. As you get closer to the top right, they're less metallic and more like non-metals. We'll use this periodic table again in a minute. But so those are all those terms, which increases from left to right. Ionization energy is the one that increases. It increases because as you go across the period, the atoms are getting more protons, making it harder to take electrons. This is energy to ionize, energy to remove electrons. Number 2 is pretty boring. Which elements in the halogen family? The halogen family is this column here. That's the halogens. Halogens, these are the alkalis. These are the alkali earth. These are the noble gases. The big area in the middle where we find all the elements that end with D, those are the transitions. And then there's a couple that have boring names like the nitrogen family, the oxygen family, carbon, boron. Those are all kind of boring names. Alkali earth, boron, carbon, nitrogen, oxygen, halogens, Halogen, Gen, and then noble gases. Hopefully you have your periodic table out as we go over this stuff. I'm going to take a moment and watch you take out your periodic tables. Yes, yeah, you. Yeah. I see you looking at your cell phone. Put that away. Get your periodic table out. Thank you, yeah. Now's the time we do that sort of stuff. Good. Okay, back here, number 3. In the periodic table, elements in the same period or row have the same shielding effect. Remember, shielding effect is the repulsion. If you're talking about any element here on the 6th level of the periodic table, it would have energy levels 1 through 5 inside of it. So like cesium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, 6. Nope, I skipped one. 5s2, 4d10, 5p6, 6s2. Whew. And so cesium is, or actually barium. I did barium. Barium 6s2. And I noticed this is actually noted 6s. This would be cesium 6s1, barium 6s2. The pattern follows the arrangement on the periodic table. 1s here, 2s here, 2p's are there, 3s, 3p's, 4s, 4d, 3d's. Oh, those are off. Those are actually the 3d's, not the 4's, even though you're 4 layers down. You have off-Bose order on the back of your periodic table, but it matches up with what's on the periodic table. So the question we were just looking at was a shielding effect, and every element in this period has the same beginning. Every element in that period goes all the way up to 5p6. It's got all of these energy levels all the way up to 5p6. And then there might be a little variation on the end, but not much. So they're all shielded by this first 5 layers from the nucleus. What else do we have? Oh, we actually have another explanation of shielding effect here. Here's an example of sulfur versus sodium. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p2. Sodium is 1s2, 2s2, 2p6, 3s1. And so they both have, and here's a Bohr model version of the atom. They both have a nucleus, 2 electrons, 6 and 2, they 8 electrons. The sulfur has these 4, whereas boron only has 1, but the inside hasn't changed for either one of them. Both of them have the 10 electrons on the inside layers, and the outside layers are different, but shielding effect is really about these inside layers pushing the outside layers out. And so the shielding effect comparing 2 elements in the same period is the same. This outside layer, it's a term we used in the notes, is the valence. The inside layer is the core. So you have core versus valence. Next page. Oh, here's our giant periodic table, which is pretty cool. That allows us to kind of see the sub-levels and everything as we work our way through. I should move that off. As we work our way through electron configurations. This is also really, really helpful when you do noble gas configurations. If you had to do the noble gas configuration for calcium, instead of having to write the whole thing out, 1s2, boom, and then 2s2, and my handwriting's pathetic. Let's just start that over. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. There we go. That's calcium. Instead of writing the whole thing out, you could notice that calcium, which has 20, argon is a noble gas right before it. Argon is up to 3p6. So if you said argon 4s2, you have the noble gas configuration for calcium. Both of these answers that I've written down here represent calcium. The longhand is the electron configuration. Electron configuration. The shorthand is the noble gas. It always is based on a noble gas. If I was trying to do 10, I would have to go back. I'd go all the way back, miss past all these to this noble gas. Start with krypton and build from there. If I was trying to do oxygen, I would start with helium. That really wouldn't help you much. If I was trying to do iridium, we don't usually do iridium, you'd go all the way back to number 54. If I was trying to do disopremium, whoa, 58, 57, you would also go to xenon because that's the noble gas before it. We don't ever stop here in this area. I'm not actually going to ever ask you a question about an element down there because that area is kind of wacky. There are tons of exceptions to the whole Aufbaus order. We're going to pretend those exceptions don't exist and just move on with our lives. Number 4, how does magnesium compare with sodium in terms of the following properties? So which element has a larger atomic size? Magnesium versus sodium. Magnesium versus sodium. So they both have the same shielding, equal shielding, but magnesium has more protons. Magnesium has more protons, so it's going to actually pull its electrons in a tiny amount. The magnesium would be smaller in size. Magnesium would be less than sodium. because magnesium has more protons to pull its electrons in. Which has more outer shell electrons? Magnesium is S2, sodium is S1, so magnesium has one more. Again, you can tell they are 1, 2, 3 layers down on the periodic table. In the S area, sodium is in the first column, so it's S1. Magnesium is in the second column, so it's an S2. Higher ionization energy. This is, again, energy to take electron, ionize it to take it. Magnesium, because it has more protons, would be harder to steal from. What are the common ions they form? So this, we can kind of tell this based off of these answers here. Magnesium's probably going to take a +2 because it has 2 on the outside. Sodium has 1 on the outside. It's going to lose 1. When they do this, they gain and lose electrons to emulate one of the noble gases. And so magnesium and sodium have 11 and 12 electrons there. And so 11 and 12, which of these noble gases is it closest to becoming? Is it closer to becoming like neon with 10 or to argon with 18? Yep, you in the sweater? Yep, okay. So what she said, well, magnesium has 12, and 12 is a lot closer to 10, so that makes sense. We're probably going to try to go from 12 to 10. Well, how would magnesium get from 12 electrons to 10? Magnesium would lose 2 electrons. And it gives away 2 of those electrons. It gets down to having 10 electrons like neon. And it's achieved what we call that noble gas configuration, which is a really stable arrangement for elements and their electrons. And we see this in nature a lot. And we're going to talk a lot about noble gases and how important they are in the next chapter when we do bonding. Which element is smaller in size? You can look at their placement. Neon versus xenon. Neon versus xenon. Neon would have way less energy levels, so neon is smaller. Indium and iodine, that's a tricky one. Indium and iodine, they're on the same energy level, so they have the same shielding, but this has 53 protons, which is going to make it smaller. It's going to pull the electrons in. Sodium and cesium, sodium has way few energy levels, so it's definitely smaller. Fluorine and strontium. This one's a little tricky. Let's see. Oh, wait, no, it's not. Fluorine and strontium. So strontium's here, go up and get smaller, get smaller, get smaller. And then as we go across, we're gaining protons to make them smaller, 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 smaller. So fluorine would be drastically smaller than strontium. It's smaller because there's less energy levels, and it's smaller because within this energy level, there's more and more protons to pull it in. And then bismuth is bigger and chlorine's bigger for reasons we just kind of discussed. Here is another periodic table with the emphasis on where we can find the P's, the D's, the S's, and the F's. So you see first layer, second layer, third layer, fourth layer, fifth, sixth, seventh. Notice as you go through this is wrong.
This is wrong. Alert, alert. This is wrong.
I feel bad for putting this on the board right now. What number should this be? Look at your Aufbau's order. It goes 1s2, 2s2, 2. No, teacher, write things wrong. 3s, 2p, right? And then you go through this one, you go through this one, you go through that one. 3p, 4s. What comes after the 4s in Aufbau's order? Yep, you take that hat off. You're not supposed to have a hat on in here. Yeah, you're right though. It's the 3D. The 3D comes next. This is a error on this one. I'm sorry. This should be a 3, and that should be a 4, and that should be a 5, and that should be a 6. Oh my gosh, I can't believe I have this on the board right now. Those D's are always less by 1. So you go the 4s, then the 3Ds. You go the 6s and the 5Ds. They're always one value less than the S's right beside them. And we'll point out that it goes 4, 3, back to 4. 5, 4, back to 5. Oh, I can't believe that's wrong. That irritates me. Number 6, which element would have lower ionization energy? Again, you can kind of look at their position. A little note in here: the larger its atomic size, the smaller its ionization energy. If it's a big element and its electrons are far away, they're easy to take. So carbon, arsenic, calcium, rubidium, radon, strontium. How does chlorine compare to bromine in terms of atomic size? Bromine's a lot larger than chlorine. Why would bromine be a lot larger? Well, look at their positions. You got your periodic table out. Bromine and chlorine. So bromine is an extra energy level, so it's definitely going to be larger. All right? So chlorine's 2p5, bromine's 3p5. It's a lot larger. Which has more outer shell electrons? This is a trick question. Both of them have 7. Both of them have 7. How could we figure that out by looking at the periodic table? Well, they're both in the P5 column. All right, so every element here is P5. So it's outside for chlorine. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So bromine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. So the outside is 2 and 5. That's 7. And the one for bromine is 4s2, 4p5. Again, that's also 7. Why don't I include the 3D in the outside layer? Why isn't that 3D included in the outside layer? Yep. Oh, you have goggles on. Okay, well, the homework's not that dangerous, but okay. So, yeah, the guy with the goggles says this is the third energy level. This is the third, this is the third, and fourth energy level. The fourth energy level is the outside for that particular atom. Where the first, the second, the third, the third, those are on the inside, not the outside. And when we're looking at this question here, where were we? Right here. Which has more outer electrons? Only the outside, the S's and the P's. I mess up? No? I messed up here. Messed up right there. That should be 4s and 4p. And that should be 3s and 3p. Oh, man, how many years has that mistake been on there? That's not good. Which has a higher ionization energy? Chlorine is larger than bromine because its size is smaller, and they both form -1 ions. Why would they both form -1 ions? Both of them. Well, okay, let's do what we did with the other guys a second ago. Let's get rid of all these annotations, and so like here they are right here. So, is chlorine closer to argon or is it closer to neon? It's between the two of them. It is far closer to argon, and it only needs 1 electron. So chlorine with 1 extra electron would be like argon. And then for bromine, is bromine closer to krypton or is it closer to argon? Bromine gains 1 electron, and it has the same as krypton, the noble gas. Charges are always dependent on how far away they are from the noble gas. So let's pick a random element. Strontium. Strontium has 38. Is it going to go for krypton or xenon? 36 or 54? You and the Batman socks. Yeah. What? Okay. So he says so strontium is 38. 36 is a lot closer to 38. So strontium would lose 2 electrons and become a +2 charge. and to look like these noble gases. And that's what elements do. That's why when we were looking at the periodic table last chapter, we added common charges. We said these are plus ones, these are plus twos, that these guys can change. They're pretty irritating. We have the plus threes, no charge because they already are noble gases. They don't gain or lose them. The minus ones for the halogens, the minus twos for the oxygen family, minus three. And these might be plus 4 or minus 4. They could gain 4, 1, 2, 3, 4, or they could lose 4, 1, 2, 3, 4, and kind of be happy. And they tend to, those guys tend to kind of switch as you go down. These tend to gain, either lose. So this side tends to be the plus 4, this side tends to be the negative 4. Why is that? When this one loses 4, it's giving away its valence electrons, these 4, and they're very far away from the nucleus, so they're easy to lose, whereas these are close to the nucleus, so it's easy to gain because they're so strong. That was a little too in-depth, even for me. Okay, what's next? Oh gosh, another version of that weird periodic table. What is a noble gas configuration for calcium? So instead of having to write down everything, you could look at calcium's position. Calcium is right here on the periodic table. The noble gas that comes before it is argon. So instead of having to write down 1s2, 2s2, 2p6, 3s2, 3p6, you can just write down argon in brackets, and then the difference, argon with the 4s2 on it, makes a calcium. So I do occasionally see kids jot this pattern down on their periodic table, but please keep in mind that the periodic table we give you will be blank. It won't have any of your fancy notes on them, nor will it have any of your drawings. So that's good because, well, let's just leave it at that. What else do we have here? Give the name of the family. Those are the names of the families that those elements are in. All right, fantastic. Which atom is smallest ionization energy? This is really also a question of which element is the largest. The larger the atom is, the farther away its electrons are. And if the electrons are far away, it would take less energy to take them. So of those elements, barium, magnesium, and chlorine. And I think I'm going to go back here. I like this one way back here the best. So that was barium, magnesium, and chlorine. Which of these elements would be the largest in size? Yep, SpongeBob shirt. What'd you say? SpongeBob shirt says chlorine. Good try, SpongeBob. No. Chlorine would actually be the smallest in size. Why would it be the smallest in size? Well, it's only got the third layer worth of electrons. It's got 1s, 2s, 3s, and the 3p. But as you go across, you're gaining protons, and it's going to pull that third energy level. It's going to get contracted in. So chlorine's actually the smallest. I was hoping that you would say barium. Barium has 6 layers of electrons, so it's going to be the biggest in size. And so if it's the biggest in size, it's just 1, 2, 3, 4, 5, 6 layers of electrons. This electron out here is really far away from the nucleus, and every layer between it is pushing it away. And so to snatch that one electron, nope, couldn't did it. I was hoping I could get that one electron. To snatch that one electron wouldn't be too difficult, unless, of course, you're working with a Promethean pen. And then you can't. So maybe I just, gotcha. And now you've, taken that one electron away. And so barium, because it has all these energy layers repelling it, is the easiest one to take from of those 3. The larger the size, the less the lower the ionization energy. Where were we? We're right here. Is nitrogen minus 3 smaller or larger than neutral nitrogen? What does nitrogen minus 3 mean? That means that unlike nitrogen, it has 3 more electrons. So it would be larger because it's gained 3 electrons. In which of the atom-ion pairs is the ion smaller? In the positive pair, because what that would mean is that it's lost an electron. And so I have clearly inarticulate handwriting here. So for lithium, lithium is 1s2. Usually it's 2s1. But if it's a positive charge, it's going to lose that 1 electron. And the only thing left would be the 1s2, which is only 1 energy layer. So that lithium plus 1 would be a smaller than normal lithium. And then for calcium, calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I just wrote blah in there. If calcium's a plus 2, it is going to lose these 2 electrons, and there actually wouldn't be any 4s electrons anymore. So then it would be smaller because it would then be just the 3rd energy layer's worth of electrons. The other 2 are negative, so they'd be gaining electrons and getting bigger. What is represented by this? That is the noble gas configuration for argon. That's where all the good chemistry jokes are. They are gone. Sorry. I'm like paid by law to say that. So what did they do? They took a noble gas called neon, and they said, argon and neon, man, they look a lot alike, do they? Yeah, they do. Argon and neon are right next to each other on the periodic table. So argon, neon is here, and there's argon there. And so for argon, you could say, well, it looks just like neon, but it's got 2 more pieces attached to it. And that's what's going on there. He's saying, argon looks like neon, but it's got these extra pieces attached to it. A couple of you might want to do the simple math and just write down neon is 10 plus 2 plus 6. What is 10 plus 2 plus 6? That's right, 18. And argon is number 18. Good. Good job. Tell the valence shell and the number of valence electrons for all the following. The valence is only ever the highest energy level. I've just written down the endings of each of these using Aufbau's order or the periodic table. Calcium, I think we've hit this one a couple times. It ends with 4s2. All of the other things would be less energy. You've got a 1s, a 2s, a 2p, a 3s, and a 3p. So the 4s is the only thing that's worth anything. It's on the outside. Oh, valence means outside layers. It's the highest energy level. Radon, it's a colorless, odorless gas that gives you lung cancer. So there's always that. Radon has 6s2 and 6p6 for its outer layers. Hey, but in Aufbau's order, the 4f and the 5d are in there. I agree. But I think we all agree 4 is less than 5, which is also less than 6. So the 6th layer, so you got the 1, 2, 3, 4, which is where the 4f is, 5, which is where the 5d is, 6, which is where our s and p are. Those are the ones that are on the outside. So when this atom floats around the universe, what's going to bump into things first? Bump, 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 bump. Is that outside layer that is the 6s and the 6p. And that's the piece that we care about. And let's do something like this. Boom. Goodbye. Phosphorus ends with 3s and 3p. There's 5 electrons there. Sulfur ends with 3s2, 3p4. There's 6 electrons there. Magnesium only has a 3s2, 2 electrons there. The second? I don't know what the second means. Right, electron configurations, noble gases for the elements. So first I wrote the full thing, then the noble gas configuration. Again, how do we do these noble gas configurations? Oh, no. The noble gas configuration, you should look at the noble gas that came before it. So for strontium, strontium is here. In case you can't see where I'm pointing, right? No, earthquake. Strontium is right there, right? And so you'd go to the noble gas that's before it, and the noble gas that's before it is this element right here, which is krypton. And then you could say, hey, it looks like krypton up to the 4p6, and you just tack on that little bit. So that's what I did. Selenium also, you go to the previous noble gas. I accidentally typed up silicon. This is silver, so let's do silver. Silver is right here. So it's in the 4D area. So we see that it ends with 4D. It's the 9th one over, which is why it ends with 4D9. Not 49, but 4 sub-level D, element number 9. 4 sub-level D, element number 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be a D1, a D2, etc. That's a D9 because it's the 9th one. And then you go back to krypton for the noble gas configuration yet again. Match, set, point. All right, match the people with the things they did. There we go. And what does all this stuff mean again? Hey, you need to know the terms, know the terms, know the terms, know the terms. Some people are really good at learning terms, other people are not. When we say energy levels, we're talking about these coefficients. Look at them all. 3, 2, 4, 3. Those are the energy levels, and they kind of give us the distance from the nucleus. The sub-levels are the S, P, D, and F, and they represent specific shapes. And I actually found someone who had pictures of all the shapes, and look at those guys. Those are beautiful. Man, look, we have the S, which is a sphere, the P, which I usually say looks like a peanut, but it is like 2 lobes on the axis. I said lobes. The D's, there's 5 shapes, and each of these can hold 2 electrons, and the F's, there's 7 shapes, each of those can hold 2 electrons. One gentle reminder that we were doing, look at these noble gas configurations. I forgot I put this in here. So neon is 1s2, 2s2, 2p6. Neon, and sodium looks a lot like it, but it's got that. Let me zoom in so you can see what the heck I'm pointing at there. There you go. So, like silicon, and these guys all look the same up until that point. Right? All of those elements look like neon. And so the noble gas configuration is neon with that extra piece tacked on. And then once you get to the next noble gas, it shifts over. So you say, now they look like argon. What about when they form ions? All of the ion excitement occurs out here, and you can kind of tell what they're going to do ion-wise by how close they are to the noble gas. So these elements here are really close to neon, so they're going to, let me just switch the way I did that. These elements here are close to neon. These elements down here are closer to argon, and their ions follow that pattern. So sodium loses 1 electron. It loses that 1 electron is the one that's lost, and then it looks like neon. Magnesium loses 2 electrons, those 2, and it looks like neon. Aluminum loses 3 electrons, and it looks like neon. Silicon can lose 4 electrons and look like neon. Technically, it can also gain 4 electrons. If it gains 4 electrons, then it'd be silicon minus 4, and it would look like argon. On the other side, this has 5, and it gains 3, so it looks like argon, looks like argon, looks like argon. So ions form based on how close they are to looking like a noble gas. It does get a little weird in the transition area, but not to worry. The last thing I want to do before I abandon you to the lab is to talk about orbital diagrams again. Orbital diagrams were in your first homework. They were in the notes. They weren't in the second homework, but you're going to see them on the test, which is next class. So you're going to do the review sheet. for homework, which is a beautiful, beautiful thing. Practice makes perfect. At least that's what I've heard. But let's do the orbital diagram for an element. Let me just ask the class, what do you want? What element? I want to. Oh, selenium. That's okay. I guess we could do selenium. All right, selenium. We don't have enough selenium in our lives anyway. So selenium has 34 electrons, and you look at off-Bose order, and it's a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, right? Right, yes it is. And then we were doing energy diagrams, or orbital diagrams, depending on what you want to call it, for elements, and they had little boxes, and there was like a 1s2 and a 2s2 and a 2p6 and then a 3s2 and a 3p6 and a 4s2 and then the 5d. Nope, not happy with how that last one came out. Pretty good. I'm very happy with that. That's fantastic. And so we were putting electrons in these, and this is the 1s, 2s. These correspond, right, in order from least to most. Lowest energy, highest energy. These numbers represent the energy level, so low energy, high energy. And we put electrons in them. What did the electrons look like when we put them in them? You with the Duck Dynasty shirt. Yeah, Duck Dynasty is not cool anymore. Not at all. But you got the shirt on, so I'll call on you. I do. Anyway, let's put the electrons in there. We've got 2 electrons, opposite spin. 2 electrons, opposite spin. 1, 2, 3. 4, 5, 6. Got possessed by the count for a second there. There we go. Keep going. Beautiful. What are we going to do here? That's no problem. There's 10. So we're still going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I did the configuration wrong. I was wondering why that girl in the back was waving her hands at me. God, selenium is 4p4. 4p4. So sorry. So this piece here at the end, you're going to do this. 1, 2, 3, 4. Are you going to do that? No, you're not going to do that. You always spread them out before you double them up. So 1, 2, 3, 4. So you spread them out, then you fill them up, and then you move on. Spread them out, fill them up, move on. This idea of opposite spin is a reference to the Pauli exclusion principle. All right, or PEP, Pauli exclusion principle, is about spin. You may not have the same spin. Bad. No same spin. And then the old spread them out thing that we just did here, that is Hund's rule. Hund's rule. No, Hund's rule is the spread them out within the degenerate orbitals before any 2 degenerate orbitals can have 2 electrons. You spread out the electrons before you double them up. And I do like the fact that we kind of finally get to see a picture here of the mystical F's. If you were drawing an F orbital diagram, which we will never ask you, again, you would do the ups first, and then you would come back and do the downs. We don't ever do F orbitals, but you could, but we don't. All right. And this is where I say goodbye. Have a good day. No, seriously. Goodbye. All right. Bye.